Now we will talk about the distance of two chords from the center of a circle. Let me draw a circle with center O and two chords AB and CD. To find the distance of chord AB from the center, we draw a perpendicular from the center onto chord AB. The length of segment OE will be the distance of chord AB from the center of the circle. And to find the distance of the chord CD from the center, we draw a perpendicular from the center onto chord CD. The length of segment OF will be the distance of chord CD from the center. We will talk about these two distances, OE and OF. What if the chords AB and CD are equal in length? If they are equal, then their distances from the center will also be equal. Basically, if AB is equal to CD, then OE will be equal to OF. This is what the theorem says. Equal chords of the circle, in this case chords AB and CD, are equidistant from the center. That is, the perpendiculars are equal. The proof of distances being equal is very straightforward. This is the figure we have. We can see two chords AB and CD with their distances OE and OF. Let's jot down what's been given, what we need to prove, and then of course the actual proof. According to the theorem, we have been given that chord AB is equal to chord CD. That's all. That's the only information we have. And we have to prove that OE is equal to OF. We need to prove that their distances from the center are equal. Now it gets interesting. The best way to prove two lengths equal is by proving their respective triangles congruent. And as usual, we see no triangles, which means we need to construct to form two triangles. That's the question we need to answer. How do we form two triangles? Let's join OA and OC. OA and OC. This bit of construction forms two triangles, triangle OEA and triangle OFC. If we prove these two triangles congruent, we can say that OE is equal to OF since they will be corresponding sides of congruent triangles. Let's get to the proof now. We look at triangle OEA and triangle OFC. Both the triangles are right triangles, and guess what? The hypotenuse of both the triangles are also equal as they are the radii. So it's very likely we will be using the right triangle hypotenuse side condition to prove the triangles congruent. But apart from the hypotenuse, which are the other sides we need to prove equal? OE and OF are eliminated since they are the ones we want to prove equal. So only sides AE and CF remain. If we prove these two sides equal, then the two triangles will be congruent. To prove them equal, we need to know an important theorem which says that a perpendicular from the center of the circle to a chord bisects the chord. It means AE will be equal to EB, and it can be differently written as AE will equal half AB. And similarly, CF will equal half CD. This was a very important step in this proof. Without this theorem, you wouldn't have been able to prove the two triangles congruent. Now look at this step carefully. We are given that AB is equal to CD. It means half AB will equal half CD. Because the right-hand sides are equal, we can say that AE is equal to CF. We got this result as AB is equal to CD. We also know that OA is equal to OC because they are equal radii. An angle OEA is equal to angle OFC and both equal 90 degrees. In two right triangles, the hypotenuse and one side are respectively equal. Triangle OEA is congruent to triangle OFC by the RHS congruence condition. OE will be equal to OF as they are the corresponding sides of congruent triangles. The best part about this proof is that we can form triangles in any way we wish to. We can join OD and OA and compare triangles OFD and OEA, or maybe join OC and OB to compare these two triangles. Or we could have even joined OB and OD to compare these two triangles. Every pair of triangles formed would be congruent. In the second part of the video, we will look at the converse of this theorem.